Yeah, we use worms and chicken liver. So
Yeah, that should do it. My nephew uses crickets. That seems to do well.
yeah, I haven't used crickets in a while, but they work.
Yeah, you got to try.
Yeah.
Well, we should get started. Does anybody have any questions from homework before we jump into section 4.4? All right, then I'll go ahead and share Photoshop and start working on 4.4. It's got some odd concepts in it. With practice, it gets a lot easier, but it can be kind of weird when you're first introduced to it. We're looking at, again, polynomial functions and trying to find the zeros so that we can understand where this polynomial crosses the x-axis and so on. And so first, let's start with factors and create a polynomial so that you can see how that works. And then we'll take a polynomial and start breaking it down into factors. So if I say I'm asked to find a polynomial of degree 3 with very particular zeros, say 1, 3i, and negative 3i as zeros. So we need to come up with this polynomial. Well, to go from a zero to a factor, remember that x minus c is a factor when c is a zero. And so notice what we did. We just did x minus the zero. Well, they gave us 3 zeros. And recall that a third degree polynomial has at most 3 real zeros. So we've got our 3 zeros here. So now we just need to create factors out of those. So we could say, well, f of x is the product of those 3 zeros, which we create by subtracting the 0 from x. Notice this x plus 3i is x minus a negative, because minus a negative is plus. And now I can just multiply these together. And I do have to multiply these together. So I'm just going to FOIL this one over here. First outside, inside last. I'll keep the x minus 1 for now, because I need to multiply that through. So first is x times x. That's x squared. Outside is x times 3i, which is, I'll just do 3ix, which looks kind of like the word 6. And then inside, negative 3i times x is minus 3ix. And then last, negative 3i times positive 3i is not positive, but it's negative 9i squared. So taking a look at what we've got here, negative 3ix plus 3ix is 0, so those will cancel. I squared is negative 1, and negative 1 times negative 9 is a positive 9. And so what we'll do is now, I'm going to go ahead and rewrite this so it's a little more clear. X minus 1 times x squared plus 9. The I terms are gone, but now we can FOIL this one. First, side, inside, last. So first is x times x squared, that's x cubed. Outside, x times 9 is 9x. Inside, negative 1 times x squared is a negative x squared. And last, negative 1 times 9 is a negative 9. And I'm going to go ahead and rearrange these so they're in descending order of exponents, just because that's what our convention is. And there is a third degree polynomial whose zeros are these three that we were given at the start. And that's how we would solve a problem like that. And I know you've got something like that in the homework, so I wanted to make sure you saw it. But that's the process we'll use if given zeros to get a polynomial that uses those zeros. Had a couple more people come in. Let me get y'all marked present. Bill is here. I already got Eric, Honoria, and Igor. Let's add EJ. All right. Are there any questions on how to find a polynomial given particular zeros? Okay. One thing I do want to point out is that we got this 3i and negative 3i here. And you saw down here when I created the factors and multiplied those together that the I terms disappeared. And that highlights one of our rules of zeros. And that rule says if a plus bi is a zero, then a minus bi is a zero. You will always get that conjugate in there. So if you notice we had positive 3i, well, that means that negative 3i also has to be a zero. So theoretically, they could have not given us this negative 3i. They could have just given us the 1 and 3i. And we would have known because of this rule that because 3i, then also negative 3i, and that would have given us our third zero. That will always be the case. If you have the positive version of the imaginary, you will also have the negative. Or if you have the negative, you will have the positive. Another rule, similar to that, says that if a plus c root b is a zero, then its conjugate, a minus c root b, is a zero. And if you think back to the quadratic formula, where we had plus or minus the square root of b squared minus 4ac, that really highlights this and why we've got a plus the square root and a minus the square root. Well, those are the two zeros you get when you use the quadratic formula. You get a plus or minus the square root. And so that highlights that this rule makes sense. So those are the two rules we really need to watch out for when given some zeros. We know there are others that go with them. For example, we do a different polynomial here, where they say find polynomial of lowest degree so they're not even telling us what degree the polynomial should be. But it does have negative square root 3 and 1 plus I as zeros. So we know that it's at least a squared because we have two zeros. But from those last rules, we know that if negative root 3, then also positive root 3. And if 1 plus I, then also 1 minus I. So now we know it's a fourth degree polynomial because we have 4 zeros. And so we'll create our factors out of those zeros. So we'll have x minus root 3. We'll have x plus root 3. And that takes care of these two. And then we've got x minus 1 plus I for this one, and x minus 1 minus I for this one. And notice I put those in parentheses. I do that purposefully for myself so I don't forget that that negative applies to both of these terms, and this negative applies to both of these terms. I might forget to negate the second term in that in the binomial if I'm not careful with that. I am going to do a couple of things here. First, I'm going to FOIL these two, and then I'm going to rewrite these two with that negative distributed, and then I'll FOIL those. So foiling these first two, first x times x gives me x squared. Outside, x times root 3 is plus root 3x. Inside, negative root 3 times x is minus root 3x. And last, negative root 3 times positive root 3 is a negative 3. So that's the FOILed version of those first two binomials. And now I'm going to rewrite these next two. So it's x minus 1 minus I, and then x minus 1 plus I. So I've got those now. Notice also that I've got plus root 3x and minus root 3x, so those will cancel. Now, what I'm going to do is I'm going to distribute this x through. I'm not going to FOIL because I've got trinomials. FOIL only works for binomials. So I'll distribute those three. I will distribute the negative 1, and then I will distribute the negative I. And I'm changing colors. Hopefully that highlights what I'm doing. So now, with this first one, I've got x squared minus 3. That's all that's left. Now distributing the x, I've got x times x is x squared. Then x times negative 1 is negative x. X times plus I is plus xi. Distributing the negative 1 times x is minus x. Negative 1 times negative 1 is plus 1. Negative 1 times I is negative I. Distributing the negative I times x is negative xi. Negative I times negative 1 is plus I. Negative I times I is negative I squared. So that's a lot, but we're okay with that. Do I have things that cancel? I've got a plus xi and a minus xi. I've got minus I and plus I, so those will cancel. I squared is negative 1, so I've got minus a negative 1. So this is really plus 1. All right, so let's simplify things as much as we can. X squared minus 3 times x squared. Minus x is minus 2x. Plus 1 is plus 2. So now the I terms are gone, and I've simplified the first one. The radicals are gone. And we'll go ahead and distribute the x squared to all three of these. And then we will distribute the negative 3. We'll combine like terms, and we will have the polynomial of lowest degree with those two zeros that they gave us. So distributing x squared times x squared is x to the fourth. And we expected a fourth degree because we had 4 zeros. So that's good. X squared times negative 2x is minus 2x cubed. X squared times 2 is plus 2x squared. Now distributing the negative 3 times x squared is minus 3x squared. Negative 3 times negative 2x is a positive 6x. And negative 3 times positive 2 is negative 6. Got a couple of like terms right here, so I should combine those. I get x to the fourth minus 2x cubed minus x squared plus 6x minus 6. And that is my polynomial of lowest degree with the 2 zeros that they gave us to work with, knowing that because one was a radical and the other was complex, that their conjugates would also be zeros. Seems lengthy. I feel like I've talked a whole bunch right there. It's a process. Just write out those factors and then start multiplying them together. Do you have any questions on that? Okay. Now that we've taken zeros, created factors, and gone to the polynomial, let's get a polynomial and see if we can break it into factors. Yesterday, we were able to do some factor by grouping, or we used synthetic division, which was nice, and found out that if our remainder was 0, then we had a 0 and could create the factor from that. So we've got some tools that will help us. One of the things that we had yesterday that we won't have today is one of the zeros. What if they tell us that f of x equals 3x to the fourth minus 11x cubed plus 10x minus 4. And they wanted us to find the zeros. Well, what in the world are we going to do? We could start guessing numbers and try synthetic division and see what we get. But as a student mentioned yesterday in office hours, there's a million numbers out there. She's right. There are so many numbers. And so what we need is a way to simplify this a little bit so that we know what we could guess. And that's where the rational zeros theorem comes in. So the rational zeros theorem will shorten the list of possible rational zeros. And rational means it might be a fraction. So what we need to do, and I'm going to say that I'm going to call this term P and this term Q. So the rational zeros theorem tells me that rational zeros of this particular polynomial are of the form P over Q, where P are factors of this constant and Q are factors of the leading coefficient. So the possibles, and I know this is kind of weird, this is where it gets really weird, are all of the factors of P. So 1 goes into 4, so does negative 1 into negative 4. 2 and negative 2 go into 4. 4 and negative 4 go into 4. So there's our numerator. And then we need factors of 3, and we know that because it's prime, those options are 1 and 3. So that's the full combination of rational zeros. Another way to write that is all of these over 1. So plus or minus 1, plus or minus 2, plus or minus 4. And then all of those 3 over 3. So plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Those are the only possible rational zeros for this particular polynomial. And when you think about that last work we did, notice that the constant was always found by multiplying the last terms in the factors. And those last terms were all zeros. And so that really highlights that this -4 here is made up of products of the zeros, which is why this works. So now the numbers we have to guess, there are only 12 numbers to guess. We've got 1, -1, 2, -2, 4, -4, and so on. So there are only 12 numbers we need to guess. And that really shortens the list of things we need to look at. So let's go ahead and try some of this. I'm going to use synthetic division to try to find one of these zeros. Now I do notice that I'm missing an x² term. So I need to include that in my synthetic division. So I'll bring down my coefficients, 3, -11. I can't forget that 0. I've got a 10 and a -4. So let's see, I see that the sign is changing with each of these. And so maybe a positive would work. Negative might work. I'm thinking positive. And I notice the numbers go up and then they drop back down. So that might help me with picking what might work. Like if I had a 4 times 3, that's 12. That's pretty close to 11. Maybe it would work, maybe not. I kind of need to guess a little bit. Let's just try 1 and see what happens. So the process, recall, you bring down the first term, and then 3 times 1 is 3, and I just write that down, and then I add these together. -11 plus 3 is a -8. Times 1 is -8. Add 0 to that is -8. Times 1 is -8. Add 10 to that is 2. Times 1 is 2. Add -4 to that is -2. So this is not a 0. Let me use the same coefficients, and I'm going to go ahead and try -1 now. Again, bring down the leading term. Times -1 is -3. Plus 11 is -14. Times -1 is a positive 14. Plus 0 is 14. Times -1 is -14. I'm feeling pretty good about this because -14 plus 10 is a -4, which I want to be pretty darn close to. -4 times -1 is a positive 4, plus -4 is 0. So we found one of our zeros. -1 is a 0 here. So I'm feeling pretty good about that. And remember, like we said yesterday, now where I started with an x to the 4th, I've got an x³ term here. So rather than go back to my initial numbers, I'm going to now start using this quotient, the coefficients here in the quotient. It'll speed up my work a little bit. And I think that'll help. Let's see, what number should I guess? I'm guessing, let's see, just thinking it through here. If I had a 2 times 3 is 6, that'd be an 8, 2 is 16. That might work. I don't know that it will, but we can give it a shot. Let's try 2 and see what happens. Bring down a 3. 2 times 3 is 6, plus -14 is a -8, times 2 is -16, plus 14 is a negative 2. Feeling pretty good. 2 times negative 2 is negative. Oh, I've got the wrong sign, though. It was looking good, but that didn't work out for me. And you know what? I think the negative 2 isn't going to work quite as well. Let me go ahead and grab a fraction. Let's just grab 2/3. Because when I bring down the 3 times 2/3 is 2, which I like. Because 2 plus negative 14 is a negative 12, which is also divisible by 3. Negative 12 times 2/3 is a negative 8. Add 14 is 6. 6 times 2/3 is 4, plus a negative 4 is 0. So that is another 0. 2/3. So I've got 2 of those, and now I've got a quadratic. Because this was the coefficient of an x cubed, now I've got an x squared. So now I can just go straight to the quadratic formula. Let's see, do I have some room here? I do. So x will equal the opposite of b, and I've got a, b, and c listed right there, plus or minus the square root of b squared minus 4 times a times c all over 2a. So that would be 12 plus or minus the square root of 144 minus 4 times 3 is 12 times 6 is 72 over 6. So 12 plus or minus the square root of 72 over 6. And let's see, 72, do a little, it's 2 times 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. And because it's square root, I want pairs. So I've got a 2, a pair of 2s, I've got a pair of 3s. So I can take one of each of those out, and that 2 has to stay inside. So I've got the 12 still there. Plus or minus, I bring this 2 out, I bring the 3 out, and 2 times 3 is 6. As I said, that 2 was a single, so it has to stay inside. All over 6. I can factor a 6 out of the numerator. 2 plus or minus root 2 over 6. Those 6's will cancel. And so I get 2 plus root 2 and 2 minus root 2 as the other zeros. So those are the 4 zeros to that polynomial. And let me zoom out a little so we can see the whole thing here. So that's our process. And as I said, it's a little weird, and I know it is. We had a 4th degree polynomial. We needed to find the zeros. And as I said, so many numbers we could pick from, but by using the rational zeros theorem, we were able to limit the number to pick down to 12 numbers. And so we started picking until we got a 0, and that reduced the degree for our quotient, and then we used some of the other zeros to try to find another one. And once we did, and we were down to an x squared, a quadratic, we could go straight to the quadratic formula. What do you think?
It's a lot of steps to remember.
Yes, I agree. And I wish we were face to face so that I could see your faces and we could have a little more back and forth on this, because it is a lot of steps. So we took factors of the constant and put that in the numerator over factors of the leading coefficient. We broke those down, and you'll have problems where it will ask you for the list of possible zeros, and so you'll have to do that. Factors of the constant over factors of the leading coefficient, and list all of those out. Notice that sometimes we guess wrong, and that can take a while. But don't always go back to that first list of coefficients. That'll take forever. And think about these last two we got. You're never going to guess 2 plus root 2. Well, I shouldn't say never. Maybe you will. I would never guess 2 plus root 2 and 2 minus root 2 as zeros. I just wouldn't do it. And so I like to use the rational zeros theorem until I can get down to a quadratic. Because I like the quadratic formula. I can plug in and I can get the i's and the square root that way. I'll leave that to help me get those. But I like the rational zeros to get down to the quadratic. Now let me show you something else that might make this, well, it might speed it up a little once you're in the middle, and that's Descartes' rule of signs. So what I'm going to do is I'm going to see if I can keep the rational zeros. I want to write the zeros down though, because I want to fill the space down below here with something else. So I'm going to write, we had -1, we had 2/3, we had 2 plus root 2, and we had 2 minus root 2 as our zeros. So now I want to clear up some space here. Those are still there, so I can get back to this work if we need to. I'm on a different layer, so we can do this. Okay, and what I'm going to talk about now is Descartes' rule of signs. Descartes, you've probably heard of him. He's the guy who said, "I think, therefore I am." But he looked at this polynomial division, basically, and said there's got to be some way to tell what sorts of zeros we've got, whether they're positives or negatives and so on. And so we count sign changes. In f of x, and then we count it in f of negative x. And these the sign changes in f of x give you positive zeros. The sign changes in f of negative x give you negative zeros with change. But let's see what we've got here. So let's see, we start at a positive and we go to negative. There's one change, and then positive, and then negative. So we had 3 sign changes. Now let's look at f of negative x. So we would have 3 times negative x to the 4th minus 11 times negative x cubed plus negative x minus 4. And a negative raised to an even power is a positive. So this would stay 3x to the 4th. A negative raised to an odd power is negative. So this becomes positive 11x cubed. This would be minus 10x minus 4. Now, how many sign changes do we have here? It goes from positive to positive, so no change, to negative, there's 1, and stays negative. So we only had 1 sign change in the negative, which means once we found -1, there are no more negative zeros, which is great. Now, all these negatives I can ignore. and I just cut the number of possibles. Well, this first one I already found, but all the others I can remove. And then the number of possibles is reduced down to 6. Now I did say there's one change here, and that is, I'm going to make a little table here. So we've got, let's see, we've got positive zeros, we've got negative zeros, and we've got imaginary zeros. So we found 3 positives, 1 negative, and we know that we need 4 zeros total. So 3 plus 1 is 4. That means there would be 0 imaginaries. The sum of each column has to equal the degree of the polynomial. Now the change is that if this number, the first number, is larger than 1, we have to consider the fact that it could be 2 fewer. So I take that 3 and I subtract 2 from it, and I get 1. 1 is not larger than 1, so that would stay. 1 plus 1 is 2. I need to equal 4, so there could be 2 imaginaries. That's the one weird thing with Descartes' rule of signs. If the number you come up with when you add sign changes is larger than 1, meaning 2, 3, 4, or larger, then you have to consider 2 fewer, as well as 3. It turned out, well, we found our 0, or our negative 1, so that worked. We found 2/3, that was positive. So it didn't differentiate here, but then we went to our to the quadratic formula and found 2 real numbers, which meant this was the combination that was true. And I know, again, that's weird too. Why do I have to consider 2 fewer? And that comes down to the fact of, like, thinking of a polynomial, yes, but a parabola, say that we've got a parabola that opens like that. It's an x squared, right? Because it's a parabola, but it has 2 imaginary zeros. And so I think Descartes was trying to handle cases like this when he came up with this rule. While x squared should expect 2 zeros, we might have 0 positive, 0 negative, and 2 imaginary, just like we do in this particular graph. So we have to consider that. But Descartes' rule of signs will make it easier for us to find out which of the rational zeros really does apply. Once you find one, it can really limit what's left. Let me show you another example. This will help, I think. Okay. So I'm going to go ahead and hide those. Let's grab a polynomial. Say p of x equals 2x to the 5th minus 5x squared minus 3x plus 6. Okay, so how many sign changes do I have? It goes from positive to negative, that's 1. It stays negative, and then it comes back to positive. So we have 2 sign changes. Now let's look at p of negative x. So we would have 2 times negative x to the 5th minus 5 times negative x squared minus 3 times negative x plus 6. A negative raised to an odd power is negative, so negative 2x to the 5th. Negative raised to an even power is positive, so we would have negative 5x squared plus 3x plus 6. Sign changes here, goes from negative to negative, so that doesn't change. So positive is a change and stays positive. So we have one sign change. So in our table, we've got positive sign changes, negative sign changes, and imaginary sign changes. We know that because it's a fifth degree, the sum of our column has to be 5. We found 2 sign changes with our initial function. We found 1 sign change with p of negative x. The sum has to be 5, so this would be a 3. I'm sorry, not a 3. Why did I say that? 2 plus 1 plus 2 is 5. Now you're questioning the value of having me as a teacher. All right, so because we have that 2 and the 2 is greater than 1, we have to consider 2 fewer. 2 minus 2 is 0. 1 is not greater than 1, so that would stay. And the sum has to be 5. So those are the potential signs, or the potential signs of the zeros. Now look at this. This is kind of key, and it's important here. We've got 2 and 0 as our positives. Let's do our rational zeros theorem, our P over Q. So 6 was our P, so that has factors 1, 2, 3, and 6. Our leading coefficient is 2, so we've got plus or minus 1 and plus or minus 2. Notice this. If, when I'm guessing, I find a positive 0, that means this is not the column for me, because that had 0 positives. That tells me that this would be the positive. This would be the right column. And so if I found 1, I know there's another one out there. If I find one negative 0, I know there's not another one, because in both of these columns, there's only one negative 0. So that's how this Descartes' rule of signs will really help me with my rational zeros theorem to find the zeros of the polynomial. The two together have to, you want to use both together to really simplify your guesses. Again, you're still guessing, but now they're logical guesses. They are based on good foundation rather than just picking some wild number. And we could continue on and guess the zeros. Might be kind of fun. But before we look at that, do you have any questions on Descartes' rule of signs? All right. Let me do one more because the table gets a little bigger with this one. I want to show you how it works. I don't want to leave you hanging. We don't have much time, so I'll kind of go quickly. Again, P of x. Let's say 5x to the 4th minus 3x cubed plus 7x squared minus 12x plus 4. Looking at sign changes, we go from positive to negative, negative to positive, positive to negative, negative to positive. That's 4 sign changes for the positive. Now let's look at P of negative x. All it does is change the sign of the terms with an odd exponent. An even exponent will stay. Odd exponent changes sign. Even exponent stays. Odd exponent changes. Even exponent stays. So sign changes are 0. Didn't change once. It's all positive. So our degree is 4. So the columns need to add to 4. We've got positive, we've got negative, we've got imaginary. So 4 positives, 0 negatives would mean 0 imaginary, because the column has to sum to 4. 4 is greater than 1, so I need to consider 2 fewer. 4 minus 2 is 2. We would keep the 0. The column has to add to 4, so this would be a 2. 2 is still greater than 1, so I have to consider 2 fewer than that. 2 minus 2 is 0. 0 stays. Column has to add to 4. So I've got those 3 options. Quick look at P over Q. 4 is the P, and so that's 1, 2, and 4. Q is 5, so that's 1 and 5. Those are the only factors. Notice I've got 0 negatives. So I am going to ignore the negatives. So 1, 2, 4, and then those over 5. 1/5, 2/5, 4/5. Those are the only possible rational zeros. And so I could start picking those 6. I could do all 6 of them even. If I get even one, if even one of those works, this column is wrong, because that column says 0 positive. So if I get 1 positive, I know that that column is wrong. And I can keep working from there. And we're actually out of time. But I wanted to highlight this so that you can see another example of how this really speeds up your guesses and makes it a lot easier to find the zeros of a given polynomial. We only covered section 4.4 today, but I didn't want to go even faster through this because the concepts are so different from, well, most anything we've ever seen. So I wanted to take the time for this. We have 2 more sections to cover in this chapter, 4.5 and 4.6, and remember we are testing this weekend. So make sure you don't get too far behind. Get that homework done. Hopefully you're at least working on 4.4 tonight so that you can get everything done in time to take the test. Again, it will start Thursday morning, basically at midnight, and go through Sunday night at midnight. So you'll have 4 full days in which you need to find the time to sit down and take that test over chapters 3. Are there any questions before we call it a day? All right. Get started on the homework. Practice doing this. I know it's potentially a long process and it's got a lot of steps to it, but as you practice that synthetic division and finding these potential zeros, I think you'll find it's going to start to speed up for you. So it should work pretty well. All right, let's call it a night. I hope you have a good one. Eric, good luck fishing. I hope you catch a good one.
Thank you. Appreciate it. Have a good one.
Thanks. You too.